So welcome everyone to our current lecture on algorithms. We have finished talking about graph algorithms, pretty much. You still have your final project on the graphs, but today we will talk about a relatively common problem, especially in job interviews, but also in overall industry. It's called two-sum problem. Again, it's also related to your data structures homework, by the way. So, and also we'll see how this problem generalizes to so-called k-sum problem, meaning, well, what it is, we'll find out, but it will involve basically finding whether some numbers add up to a specific target number. A relatively simple problem, but it can lead, and solving it can well involve all the tools we've been learning this semester. So let's take a look at it, and I'm sure some of you have already maybe seen it, right? Who has seen two-sum problem?
I think so.
You too, right? So again, always double checking if maybe somebody has seen, because again, it's pretty popular topic, but we'll see how deep can we go into this, how well can we do. So let's get started. And so again, of course, you can do it in a Colab, but I will be using GitHub, right, as well. Of course. Probably need two-factor authentication, as usual. No, obviously it changed. So no time to steal credentials. All right. By the way, have I turned this on? I didn't. Yeah, everything's good. Right. Now let me go time. And again, as usual, we'll be using code spaces. I'll be using code spaces. But this also should be working. It should work also in a Colab if you don't have, well, if you for some reason prefer Colab, right? And let me see here. And we'll go to code space. Let's spin up the virtual machine. And we'll start with maybe even easier problem, even though it's not that easy, but and I'll be using my favorite application, Paint. All right. So our topics. Solving. Looks like it's kind of slow this morning, but we'll see. Smaller. All right. So, a two-sum problem basically is given array of integers, return indices of these two numbers, whether they add up to a specific problem. I'm just trying to see actually now why is this is not. I guess I must not have. No, wait. The Colab is correct, right? Solving two-sum. This is correct, and I'm looking at it's weird, code space is not reflecting the newest additions. That's interesting. I wonder why, right? Solving two-sum, right? And the code space is like on a few days old, right? So it's interesting. But I guess we could use a Colab then for now. All right, yeah. So, but let's start with a simpler problem. You have an array of numbers, and you have a really simple task whether any two numbers add up to 0, right? So something like this, I will type up a nice little list of numbers, right? Maybe let's do 5, 2, -5, right? 3, 6, 7 and minus 6 or something like that. Okay, right. Okay, let me. Right, something like this, right? So, and you want to find your target, right? Your target, right? You want to just you want the 0, right? Oops, where's my drawing today? Right, so here we go. Right, so you want 0, right? We'll make it a little fatter, right? Let's make it a little fatter. Oh, come on. There we go. Big fat 0, right? So, I mean, how do we solve this problem, right? Well, first of all, okay, we can go through, right? Like, what's the easiest, like the obvious way of solving this?
Brute force.
Yeah, of course. Again, as I always say, when in doubt, use brute force, right? So again, if you only have about 9 numbers, right? Brute force is probably going to be enough, right? Exhaustive search, right? So how would you, how brute force algorithm, how would it work?
Well, it would take the first number and then check the sum with
Check.
every other
Yeah.
number.
So yeah, so you basically for some number, right? Maybe like this, look something like like pseudocode be like for n, for number 1, maybe I'll call it n1, right? In numbers, right? Very good pseudocode, right? And then for you check with other number, and this is of course not completely clean yet for n2 in numbers, right? Numbers, right? And if they are right, if n1 equals, if plus, right, there's probably, again, here you go, right? I'm used to, right, if n1 plus n2 equals 0, right, then win, right, win, win, right, okay, so that's brute force. So, who can tell me complexity of brute force solution? N squared, of course, yes. Why? 2 loops, right? 2 loops, and they both go through all both of the same array, right? Which is n length, right? Assuming n length, right? And yeah, because of course it might be tempting. Okay, you take a number and I'll find this right in one loop, linear, right? But obviously we don't have any sort of memory. We don't have anything telling us, right, where there's going to be minus 5. It's like obvious when you have 10 numbers, right, but if you have a couple million or a billion numbers, it's not going to be obvious. So this brute force, if you have a million numbers, it's doable. Or maybe you could run through million numbers, probably million times million, right? That's trillion, right? Could take a few, we could try it sometime maybe, but it'll probably take probably a couple hundred seconds, probably, right? I would say, right, depending on whether it's a C++ code or Python code, depends on your machine. But maybe it's doable. But if you have billion numbers, that's not going to be doable, right? Billion times billion, what is that? Quintillion? I guess quintillion or something like that, right? But yeah, so not something that's going to be done in our lifetime, probably, right? So that's the essence of problem. And again, you might begin, I like it, sometimes you ask, what is this good for actually, right? Is it actually usable besides making your brain hurt at a job interview? No, it's actually used. There's some use for this problem, right? Like in financial analysis, right? If you need to find whether there is some debits and credits, right? Of course, it will be part of some bigger problem, right? Obviously, it will not be just a single thing, right? Some error checking, maybe some offset, right? In some physics simulations, possible, right? So again, even this zero-sum problem, right? So maybe even some, game development and some offsetting, some moves. But yeah, so there are some uses, some real-life uses for this problem. Now let's see. So brute force, right? That's good. So, well, again, some of you already know the tricks of this problem, how to solve it. But let's look at some of the tools we have, right? Like a greedy approach to a problem. Well, greedy approach is just look next number. If it works, right? Yeah, we win, right? But the greedy approach is not really applicable here. What did we learn earlier in lectures? We talked about special type of algorithms, about the sorting algorithms, right? So, what would happen if we sort these numbers? Well, I guess I'll see if I can sort in my head, right? Let's sort this in my head. I'll see, right? I don't know what kind of sort I'll be using. Insertion sort, maybe. I don't know, right? Let's see this. And you'll correct me if I do it incorrectly. So -7, right? -5, right? So what do we have? 2 3s? 3, 3, right? 4, sorry, 4, 5, 5, 6, 7, 9, right? 5, 6, 7, 9. That looks correct, right? The question is this insertion sort, because I always find the minimum, right? Or selection sort. No, I'm always. Which one is which?
I don't remember exactly.
Right, we always find, I believe it is not insertion, I think it's selection. It is selection sort. It is selection sort, right? So I found the mean out of currently not yet processed numbers, right? Again, quadratic solution, but it works well enough. Okay, so we have these numbers, all right? So what could we do basically now? All right, we have it sorted, all right? So first of all, of course, again, how much time does it take to sort this thing? N log n, of course, right? It's like, yeah, in general case, yes, of course, we have some other sorts like bucket sort and things like that, but it's n log n. So, okay, we only paid n log n, so we're not going to do better than n log n, right? But hopefully we not reach this quadratic solution, hopefully. Right, so what could we do? Right, we have sorted numbers. It's like one of the, like dealing with some problem, you have some sequence of containers, you know, some sort of, array or something. Think what happens if you sort it, right? Because you know it costs n log n, right? And you only have a quadratic solution, or maybe you have a cubic solution. Maybe you can do something better if you have something sorted, right? So, what approach could we take? Well,
now we could only check with, well, technically half of the array, but only the positive numbers with negative.
yeah, okay. So how could we find the positive numbers where they start?
Well, we would have to loop through once, I guess.
We could loop through once, of course, or do we have to loop through once? Do we?
Well, not entirely.
No, we don't have to loop through, right? We have sorted. Why should we loop through once, right? What can we use? What can we use to find the, like you want to find a needle in this, right? You have sorted numbers, right? What can we use? Who can tell me? Wait, I know you know. You have sorted numbers, you need to look specific number, find a specific number, right? Yeah, but you don't know which numbers are there, but you know they're sorted, right? And you don't want to do a full search, right? What can you do? Let's say you poke in the middle. You check, okay, is this positive? Yes. Okay, is this positive? Okay. Who can tell me? You know this. I know you know this.
Well, I forgot the name of the algorithm.
Yeah.
You can check the middle.
Yes, and then middle. So you say, okay, you want to find here somewhere, right? So you check in middle somewhere, right? You know the middle, right? And it is, over 0, right? Yeah. Okay, so you go, it's still there, so you go half, right? Now, sorry, my drawing skills are atrocious. Right, so you go in middle, and then you divide and divide and divide. How do we call this algorithm? Yeah, of course, it's binary search, right? And a complexity of that is? Log n, of course, right? Because it is, you have to go through, it depends, right? As a logarithm of the number of elements you have, basically, right? So, we could use that, that's really good, right? So, we paid n log n, right? We set aside, and now we can do these type of operations, log n operations. That's pretty promising, actually, right? And maybe we could do something with it, actually, right? But let's think of something else we could do, right? We have, how about the ends of this, right? So -7 and 9, right? And now it's a max and min, right? Right? What could we do? We could compare them, right? We could compare, right?
Yeah.
Right? Well, if they are, basically, if they are match, right? We win, right? We have solved the problem, right? So the question, of course, is to see this is viable approach, right? What do we do if we don't have a match, right? Let's see, in this case, Yeah, -7 and 9.
Well, then we kind of check which has a larger
Yes.
modulo.
Well, yeah, well, or absolute value.
Yeah,
Because,
absolute value.
yeah, we can check absolute value base. So, which one is larger, right? So, in this case, this is larger, right? And we go down here. So we decrement we could say, okay, we basically move the pointer, right? Remember, these are pointers basically, right, to some array values, right? So, decrement. So, now we can check, of course, now we have the win, right? This is the easy case. I should probably add like minus 200 here, something, right? So, you see how quickly it finds a solution. Of course, this is the best case scenario, but in general case, we have these two, pointers, right? Right? And we keep moving them, right? So, how long will it take? Okay, first of all, will we always find a solution, right? Assuming it exists. We assume it's a solution, there is some solution. Well, since we always check, we know we have this sorted order, right? And we are making a single move each time, right? We can't overshoot, right, basically, right? We can't go wrong, basically, okay? So, let's imagine there's no 7, okay? I'll pretend there's no 7 here, right? There's no 7, so we don't have solution yet. We go to 6, right? Right, we didn't find a solution, there's no 7, right? So what happens then? We check -5, -6, right? So we need to, well, which pointer do we move? We move this one again, right? Moved again, and now again we find solution, right? So this is not a great example because we find very quickly, right? But yeah, so eventually, right? Eventually, you see, you can't miss the solution. That's what we want to find. But whether this algorithm, which we have not fleshed out yet, right? Whether it will find solution if one exists, right? Does it seem intuitively it will find? Probably, yeah. So show of hands, who thinks they'll find? Yeah, good, yeah. This is a case of mass. It's true. Yeah, you can find it basically, right? So now, eventually, of course, what's going to happen? So how long do we go? Do we have to go to both points have to go to the end, or when do we stop? When do we stop?
When at the section where between the negative number and positive.
Yeah, well, basically, eventually we'll meet somewhere, right? So it will meet because we can't. There's no point overshooting, right? Because we always check that, right? So wherever they meet, basically, right? The index or whatever you want to call it, right? So do you agree with this, right? More or less, yeah. Okay, right. So now the question is, of course, this algorithm. It's actually called two pointers approach, right? Right. But basically, you have two hands and you go check from both sides, basically, right? How long will it take? Like, assuming somebody gives you this sorted list, right? Let's set aside that for first. So, assuming how long will it take?
In the worst case scenario,
Yeah.
it would be O of n.
O n, right? Because
O n minus 1.
well, yeah, but again, we discard it. With minus 1, we discard it, right? Because we don't, the constant factors we don't count as far as complexity analysis, right? So then we have a linear algorithm, assuming we have sorted. Unfortunately, well, we have to sort first, right? So the complexity of this approach, assuming you have just some data which you don't know the order, you have to sort it first. So this is called two pointers approach, right? Two pointers approach. And this is already pretty good, right? So sort, right? And then while left is maybe, less than right? Check if left plus, well, how should I say? I guess it'd be hard to encapsulate this in my awful pseudocode, right? If left, absolute, I guess we can call absolute of left, right? Which if they match, right? If absolute, I guess we can do this absolute with the other approach too. Absolute of left equals, right? Absolute of right. We win, right? Win, and then we change the pointer. Else, right? Depending, we move pointers. Move one pointer. move big, I'll call it bigger pointer, this is real, so bigger pointer towards center. Again, this is like really, really not precise definition. We'll see in second part of lecture, we'll write some code as well, right? We'll see some solution. Okay, so we know this is on O n log n, right? So we got the O n square, right? And we have n log n. Okay. So question is, of course, can we do better, right? Some of you know, but can we do better? What else could we do? Right, what's the idea, what else could we do? And this is one of the big ideas in general in computing, in algorithms, in general, in solving algorithms, right? Well, maybe I'll pull up big old cheat sheet. So, and I'll tell you, this is, again, I think it would be unfair if you don't know anything about this problem, and somebody asks you this in an interview, it's kind of hard to solve, like, I don't know, in 15 minutes, I think. Right? If you get this n log n solution, I think this would be a good approach, actually. Right? N log n, not too bad, right? Use standard sorting, and this two-pointer approach is very general, right? But the second approach, actually, is also quite general once you learn it. It's also applicable, right? So, what's the big idea? Well, what is the problem with this problem here, right? We had these two loops, right? Each time we went through, we had to go again, right? We had no knowledge, right? Basically, we go through here, right? 5, we have to check every other number. But what if we somehow knew? What if we had some sort of memory of what's in there?
Like a dynamic array.
Well, not dynamic, I mean not array, some different data structure. Let me show you what I'm talking about, and I'm sure you'll figure this out. What data structure we know, right? That has a very good specific, again, so we are here, we are in bad area. I would say it's pretty decent, not, I'd say fair, but okay. So we don't want to be the horrible area, right? We want to get down here. Maybe we'll get to fair area, right? That's where we want to end up, right? But this is, again, not horrible. But okay, so there's structure operations. So what could we use for our memory, right? And assuming we have a good implementation of this data structure.
Hash table.
Yes, of course. Because why? You see these nice little O1 operations, right? We have these nice O1 operations, right? So we learn how the hash tables actually work, right? But assuming it's built well, right? We have good collision resolution, everything, right? It gives you amortized O1 performance, right? So now, okay, yeah, if you could somehow implement, so we could use this, we could build up a memory, right? So how could we do this actually, right? We have this data. I guess I'll have to copy it. I'll copy this. I'll make a new picture, right? Yeah, Control C. Let's look at my paint skills start improving. Yeah. All right, and let's do, right, there we go. Right, so idea would be this, right? So we go through general idea, right? Oops. Where's my pen? Right, there we go. So idea would be for n in numbers. Again, I need fatter pen, I think. Yeah. Numbers, yeah. If. So idea, again, pseudocode, right? Now we don't look at details and general idea. If n has complement, right? Complement in hash table, right? In hash table, right? Don't worry about my writing. We win, right? So what the question? Okay, that's good. Okay, right? But initially we don't have anything in the hash table, right? So what could we do in this case? So what's the trick here, right? Else, right? So this is the case we don't have this, right? And this is the step which makes everything work in this approach. What do? We don't find a match.
We just store the number
Yes, we have to, that's again, it kind of makes sense, right? We store the number, right? Else, store, right? Store, again, a very pseudo code, store number in hash table, basically, right? Right? And again, so because the now thing is in has complement hash table, the thing is this is O1 operation, right? And this also is O1 operation. So that's what makes it work, right? This is, of course, ON, right? Right. So this makes it work, right? So we're left with the details of how to actually write this in your language of your choice. Again, we'll do this in Python in the next part of the lecture, right? We still have some time, actually, right? So, and this is basically ON solution. And this is what typically, again, what usually people want to see this at the interview, something like this, right? Well, I think analog N solution is actually quite practical as well, but this is what interviewers want to see. But the thing is this completely, well, are there any downsides to this solution? Well,
It's not memory efficient.
yes, very good. So, what did we do? We traded space for time, basically, right? We took some space, right, memory, right, and we gain efficiency in time. So, how much memory we need? Well, whatever the hash table implementation, we can look it up, right? What's good hash table? Good hash table, space complexity, right? ON, well, of course, right? So, ON, so basically we get, it's not completely free, all this stuff, but so time is ON, right? And also space is ON, right? Right? So, okay, now you might say, okay, but didn't we need some space in previous solutions? Well, not really, right? Assuming we, sort the list in place, right? We don't really need some memory, right? We just, well, 2 pointers, right? But those are fixed, right? Only 2 pointers, right? I mean, that's just always fixed. You have billion items, still 2 pointers, right? That's fixed in size, right? So here, we actually do need the ON, right? So, if you have a, well, assuming again, if you don't have enough space maybe to build a billion item ON list, right? But it's doable again. So this is in general for 2 sum, or in this case 2 sum for targeting 0, right, or 0 sum basically, right? This is will give you the most efficient solution as time goes, right? So again, of course, you can ask, can we do better? Well, I personally don't know a better solution, but if you think about it, can we beat ON time, right? I don't think you can, because, well, you need to have the numbers, right? You don't have the information, right? So, no way around it. Could we, if we always have, well, even if we gave you a sorted list, if only somebody gave you a sorted list, right? You still end up with these 2 pointers, right, moving, so you still have a linear solution, right? You can't really escape going through the items, right? It's like no way around there. Okay, so this is a 0 sum, right, problem, the easier problem, right? Usually this problem is given as a general problem, right? Meaning, what I mean is this general problem of going to, yes, brute force, right? 2 pointers, right? Target. So basically, this is a general problem definition, right? Given array of integers, return indices of 2 numbers so that they add up to a specific target, right? So let's say here, right, target's 9, solution would be 0 and 1, because 2 plus 7 is 9. So, again, would the brute force solution change much? Not really, right? Let's see if we have it here, right? Right, you have brute force. Instead of 0, we're trying to find something else, right? It doesn't matter. We just instead we just get rid of this. If you have 0 instead of target 0, right? We could switch to something else, right? We could switch to some number, right? Maybe I don't know, a 7, right? Like 7, right? Switch target to 7, right? 7. Oops, again. Yeah, this is great, right? There's my brush, right? So we switch to 7. Target equals 7, right? And we just move it here, right? The target's here, right? target. And we still have our quadratic complexity, right? Nothing changes really, right? The brute force doesn't change, right? So I'm sure most of you will have at least a brute force solution to this problem, right? Easy, easy, easy. So the question is now about the sorting. Well, a little bit trickier, right? Seems a little bit trickier now. Start thinking a little bit, right? If things change, right? You do the. It's not absolute anymore, right? This part here will change a little bit, right? So what will change, right? You still have the 2 pointers. You start at the minimum and maximum value, right? You see whether they add up, right? And then you have to check. You need to move one of the pointers. You need to decide which one, right? You're here, right? Basically, right? And you're trying to find. You move the biggest one, I think. Yeah, let me think now. If I do it correctly from my head, right? To look at the implementation later on, we would move the bigger one to the absolute or the biggest one left. I think we move the biggest one if I remember correctly, right? Which is if it's correct. Yeah. So we move it together, and eventually again, right? We will end up a solution where we actually get to the pointers here, of course, in this case scenario. And again, a reminder that a single number, right, doesn't work, right? 0 and 7 would work, but just 7 alone is not sufficient because it's just one number, right? That's a different problem. Find a number, right? One sum problem, right? Which we know how to find, right? That's easy, right? So, which we could use binary search in this case, or we could use linear search if you had a, one sum problem is ridiculously easy, right? So yeah, so what 2 pointers, we'll need to do some work here on checking the pointers, but in general, it would be applicable. So how about the hashing solution, right? Right here, right? So this is also very, well, I would say quite tricky. The first time I saw this solution, right, I was like, wow, okay, this is kind of cool, right? This has a cool approach, right? So because we don't have a complement, right? Well, but we need to find some complement. Right? So we have a target. What kind of a target should be not obvious? Like 9, no, you don't have, 8. You don't have 8 here, right? Yeah, 8. 8 would be okay, right? Or 13. Well, let's do 8, right? So target is 8, right? Let's do target. Target is 8, right?
Instead of complement, it would be target minus n.
Yeah, basically, because we want to find the index, right? So this is, 0, 0, 1, 2, 3, 4, 5, 6, right? 7, 8, right? So in this case, we want to remember 0, 1 is the solution, obviously, right? Easy solution right here. But so we need to come up with some definition of a complement, basically, right? So because so what do we store in the hash table, basically, right? So we need the keys, right? So keys would be the value, right? So wait, or worse, you want the complement value, right? You need to find it, what it will be, right? So you check, right? So let's think how this would work. Right? So this complement function, but we've got this complement here, right? So if n has complement, what does it mean here, right? So let's say 5, right? And originally we have nothing, right? So we need to store the n in hash table, right? So this means that what do we store in the hash table, right? Originally, right? The base case, like we have nothing. So we don't have any hits in the hash table. What do we store? We store basically.
Well, we can store either 5 or 3.
Well, we don't have. Yeah, we could store either one, right? Because we want the index, right? So we want to find the index. So I would say we could store this, right? So store key, right? Key 5, right? Value 1. No, sorry, 0, right? Because 0 index, right? So that should work, right? That's the first case, right? So second time, we check the complement function. It's probably been written somewhere here, right? Basically, not enough space, right? So we have target, right? So target, we check what? Target if this complement, right? So we check target, right? Or hash, right? Hash table, or dictionary, of course, in Python, right? Hash table, or math in C++, right? So hash table, And what do we have here, right? So we have target minus or current n, right? N, right? Check it if it exists, right? Do we have a hit? So this is a trick. This is the thing that like kind of blew my mind the first time I saw this. So wow, this actually works, right? So because why? Because it's O1 operation, right? This is O1 operation, right? And if it exists, check, right? If it exists, and in this case, we find it, right? So it's going to be like 8 minus 3, right? If it exists, right? Cool, we find the match, right? In O1 time, right? So we have what? We get the 0 out, right? We get the 0, right? The value. If we find the match, we win, right? We win, we return both. Then we return both keys, both indices. Not keys, by the way, not both indices, right? Both indices, right? So we return 0 and 1. So again, we'll see this how we can do this in actual real code. Okay, right now it's just a really sort of like we're still skipping some technical details depending on your language, right? So, but do you get the idea that this should work, more or less, right? So, what's the takeaway again from this whole discussion is, right? Well, what do you think? Like, what's the moral of the story is so far?
Use hash map.
Yes, of course, yes. Use hash maps as much as possible, right? They have well-designed hash maps, right? Again, careful if they're not sorted, right? Remember, you usually don't need sorted, right? Because that's you pay extra log n operation cost, right? Usually want unsorted performance that gives you O1, you know, search, deletion, and insertion O1, right? And see if it's usable, right? Like it's like your key value database basically, right? In memory, basically, right? O1 performance, good stuff, right? So hopefully I convince you. But again, the tricky part in this whole thing, why it's also giving us problems, because this part is like somewhat non-obvious what we store. This trick here, we store the key, I think. Right? Everything else I think is pretty easy, right? But this little trick here is what sort of drives the problem, I think. All right. So what else? Right. So now that we have solved the two-sum problem, well, we can sketch the ideas. How about the three-sum problem, basically, right? So, or four-sum, five-sum, and so on, right? So three-sum, how could we solve it? Well,
Wouldn't it be similar to what we had in our midterm?
Yeah.
About the rod thing where we had to have dynamic array?
Yeah, well, basically the thing is, for three-sum we could basically we only solve the two-sum basically. The idea is we could try to reduce it, right? Maybe solve it. They have the two-sum problem solved, right? And we could try to add on top the third number basically, right? That would be the general idea. Reduce the problem to a previously known problem basically. That would be the approach, right? So that's the general idea. Again, I'm just sketching in this idea. So general, again, if you can solve it for, again, I'll do another paint, right? So general, yeah. So we call this K-sum, right? K-sum. So three-sum, right? Two-sum, right? So we know this. We have this, knock out of the park, basically. We have this, right? So, try to reduce, right? Reduce, right? So we have a, n sum to n minus 1 sum problem, basically, right? That would be the general approach, right? You know how to solve a simpler version, right, basically, right? So try to reduce, right? So again, so what we could do is sort of like kind of half brute force, go through for three-sum, we could go to like, okay, have a number and see if that number plus the two-sum solution is the solution, basically, right? That would be approach, right? So what kind of complexity will we have? We will have, assuming our two-sum is in linear time, right? We have hash table for that, right? You will get well, so
N squared at least.
yeah, n squared, right? Sadly, as far as I remember, that's basically what we can do, right? You might think, okay, maybe because we do some fancy hashing, like have a solve three sum all together. Can't really, well, maybe you come up with it, but I don't think, I don't know, right? So yeah, for three sum, basic idea would be this, right? For number, right? For n in numbers, right? In nums, right? If n plus two sum, right, of numbers, right? And of course, what two sum numbers with target would be numbers, you know, the target minus, you know, target minus n, right? You need to find that number, right? So equals, you know, equals targets, right? So equals target, right? Right, and this here, you need that two sum target would be target minus n, right? Right, this here, right? You need target here. Right, so you win on, well, and that's it, basically, right? And you keep doing it, right? You win, and fail, right? And this is fail, right? Or false, of course, right? Fail, right?
So for the k sum, the complexity would be k minus out of the n to the k minus 1?
Yes, with this approach, yes, exactly. Indeed, yeah. Easy to solve, right, in general case. The reduce, and it indeed would be k minus 1. But another question is, and that's an interesting question, I don't know if we can, if you read, there's some links to the literature. Can we do better than that? What do you think? There is, interestingly enough, the author of our course materials, Jeff Erickson, right? He actually has, he's one of his pet theories, right? He has a better approach, actually, right? We'll see if that, so it's kind of not obvious immediately, how could we do better than this, right? Let's say you have a large k, right? But remember we have our friend divide and conquer, right? Maybe we could do something with that. Maybe we don't have to solve always k minus 1. Maybe we could do something trickier, maybe a little bit, right? He has an interesting approach, and it's like not completely obvious immediately, right? But the idea would be to solve only, you know, half-sized chunks, basically. Like, you know, you need to find 8 sum, right? You solve for 4 sum and 4 sum together, basically, right? So then it means you gain the complexities only to the n to the 4th, not to n to the 7th, right? So that's the promise, right? I don't know if we'll get there, right? Today, probably not. But there is an algorithm, actually, which solves it actually in less than k minus 1, right? You know, so idea here, yeah, so in this solution, like correctly point, so this is in general case, right? In general case, so O, you know, k minus 1, basically, right? Of course, right? N of course, right? N of course, right? so n to k minus 1. So you have 8, right? You know, 8 sum, right, would be O n to the 7th, right? So n to the 7th, that's kind of bad, right? That's pretty, you know, not feasible, right? And in fact, there is another problem which we have not yet touched here. It's called subset problem in general, right? Very famous problem as well, which has basically, you need to find whether there exist, you have some numbers, whether any number of these numbers add up to this target number, right? And that's much harder problem to solve, right? You don't have any good linear polynomial time algorithms for that problem. That's much harder because you could pick any number of numbers, basically. You know, 5 or 10 or 15, right? That's much more open-ended, right? That's much harder problem, right? This one, we have specific numbers we can use. That's easier, right? If you don't know how many we can use, right? 1 or 500, right? That's much harder because you don't know, right? You have to check everything, right? So you know, it's almost, well, it seems almost impossible, and it is harder, right? It has been not proven that you can solve this in polynomial time, right? So it's called actually an NP complete problem, actually, right? So a hard problem. But this one, you can have k minus 1. So let's see, we have, I think, time for break. By the way, speaking of breaks, You heard this morning there's going to be a siren at 10 o'clock, right?
Yep.
Yep. So let's start at 10. Well, we can be here at 10, but we'll start at 10:03, I guess, right? So it will be, right. Yeah. Yeah.